In April of 2019, the world watched as scientists unveiled the first ever photograph of a black hole, a hazy orange ring of light wrapped around a perfect circle of darkness, 55 million light years away, at the heart of a galaxy called M87. It was hailed as one of the greatest scientific achievements in human history, splashed across the front page of nearly every major newspaper on the planet, and celebrated by scientists who had spent their entire careers chasing exactly this kind of direct visual confirmation. But buried inside the physics papers that followed that historic announcement is an admission most headlines never mentioned, buried in dense technical language that rarely made it past the scientists and specialists who actually read the full published research. The picture scientists took doesn't actually prove they photographed a black hole at all. It proves they photographed something. And there's a real, serious, ongoing scientific debate about whether that something might not be a black hole in the way we've always imagined one. Like and subscribe if you want to keep following this story, because what's hiding inside that famous orange ring is stranger than almost anyone realizes. To understand why this question is even being asked, you first need to understand exactly what the Event Horizon Telescope actually captured back in 2019. It wasn't a single telescope in the traditional sense. It was a coordinated network of 8 radio observatories scattered across the planet, from Hawaii to Spain to the South Pole, all linked together and synchronized with atomic clocks to function as one massive planet-sized virtual telescope. Building an instrument like that required years of painstaking coordination, precise timing, accurate down to fractions of a second, and enough combined data storage to fill hundreds of hard drives, all of which had to be physically flown to a central processing facility because the sheer volume of raw data was simply too large to transmit over the internet. That network pointed itself at M87, a giant galaxy sitting roughly 55 million light years from Earth, and captured radio waves streaming from the extreme environment surrounding its central object, an object with a mass of about 6.5 billion times that of our Sun, an object so massive that its gravitational influence shapes the motion of stars across the entire central region of its host galaxy, an object scientists have named M87 star. What the telescope actually recorded was a bright ring of glowing plasma, superheated gas swirling at incredible speeds, reaching temperatures of billions of degrees as it spirals inward under the pull of the central object's immense gravity, surrounding a dark beyond which nothing, not even light, can escape. It's the shadow cast by whatever gravity that it either falls in or gets redirected away from our line of sight, leaving behind a dark silhouette in the middle of the glowing size of that shadow is consistent with a black hole, but it isn't unique to one. If you're just discovering this channel, make sure you like and subscribe, because the next part of this story is exactly what serious physicists have been quietly debating ever since that image was released. In the official scientific papers published by the Event Horizon Telescope collaboration itself, researchers dedicated an entire section to a category of objects they call black hole mimickers. These are theoretical, exotic, compact objects that, according to general relativity and several alternative theories of gravity, could produce a shadow strikingly similar to what M87 star actually showed, all without possessing a true event horizon at all. This wasn't a passing footnote either. It was treated as serious enough to warrant systematic, methodical testing against the real data. The researchers systematically worked through several categories of these alternatives, including black holes modified by additional fields, compact objects predicted by alternative theories of gravity, and a particularly fascinating class of object called Boson stars. A Boson star is not made of the ordinary matter that makes up stars, planets, or even black holes, as most people imagine them. Instead, it's a theoretical object built entirely out of a hypothetical class of particles called bosons, held together purely by gravity and a delicate quantum mechanical balance, rather than the nuclear fusion that powers ordinary stars. Physicists first proposed the mathematical framework for boson stars decades ago, largely as a theoretical curiosity, a way of testing what kind of stable self-gravitating structures the equations of general relativity might permit beyond ordinary matter. Unlike a black hole, a boson star has no hard surface, and crucially, no event horizon at all. Light isn't trapped or destroyed when it reaches a boson star's core. It simply passes through, bent along the way by the object's immense gravity, but never permanently lost. And yet, according to detailed simulations performed by physicists studying exactly this question, a rotating boson star surrounded by a ring of superheated, swirling plasma could produce an image astonishingly similar to what the Event Horizon Telescope actually captured at M87, a glowing ring wrapped around a dark central region, almost indistinguishable at first glance from a genuine black hole shadow. This isn't some fringe idea circulating only on obscure corners of the internet. It's a legitimate, peer-reviewed area of theoretical physics, studied by research groups at major universities and institutions around the world, published in respected astrophysics journals, and presented at international conferences dedicated entirely to strong gravity physics, work carried out by physicists who spend their careers testing exactly this kind of question against the harshest available data. Researchers have explicitly stated that, due to the striking similarity between simulated Boson star shadow images and the real images obtained of M87 star, it might be genuinely difficult to definitively rule out Boson stars as an alternative explanation using current observational data alone. In other words, the mathematics and physics of an exotic, horizonless object can, under the right conditions, mimic almost everything the Event Horizon Telescope actually measured. So, why hasn't this alternative explanation made bigger headlines? Partly because the Event Horizon Telescope collaboration itself did rigorously test several of these alternative involved, running enormous numbers of simulated images through supercomputers, and comparing each one, pixel by pixel, against the real observational data gathered in 2017. Certain categories of exotic black holes surrounded by unusual scalar field configurations, for example, would be expected to produce extra lobes or disconnected dark patches within the shadow, features that simply aren't present in the real M87 image, allowing researchers to rule those specific alternatives out with reasonable confidence. Other proposed alternatives, including some models involving ultralight boson dark matter particles, theorized to explain dark matter distribution on galactic scales, were also constrained and in some cases disfavored once researchers combined the Event Horizon Telescope's mass and spin measurements with other independent astronomical data, narrowing the range of particle masses that such dark matter candidates could plausibly have. But boson stars, along with several other categories of what physicists call horizonless compact objects, have proven far more stubborn to eliminate entirely. This broader family of alternatives also includes gravastars, hypothetical objects with an ultra-dense but exotic core supported by a repulsive form of vacuum energy instead of the crushing singularity predicted at the heart of a true black hole and wormhole-like structures, exotic solutions to Einstein's equations that could, in principle, thread through to another region of space-time entirely. Researchers studying rotating boson star models have specifically noted that the size of M87 star's shadow, based on independent mass estimates derived from how stars orbit around the galactic center, is actually too large to match a simple, non-rotating boson star model. That finding rules out the very simplest version of the boson star hypothesis. However, more complex, rotating boson star configurations remain much harder to eliminate, precisely because their predicted shadows can be tuned through different internal parameters to closely resemble what was actually observed. This is exactly the kind of scientific uncertainty that rarely makes it into a 2-minute news segment, but sits right there in the peer-reviewed literature for anyone willing to actually read it, a gap between what gets reported to the public and what actually appears in the technical record that shows up again and again across many areas of modern astrophysics. The current scientific consensus, held by the overwhelming majority of astrophysicists, remains firmly that M87 star is a genuine black hole, and for good reason. General relativity has passed every major test thrown at it for over a century, from the bending of starlight during solar eclipses to the direct detection of gravitational waves rippling outward from colliding black holes, and a true black hole remains by far the simplest, most well-supported explanation for an object of this mass, size, and gravitational behavior. But even mainstream researchers directly involved in the Event Horizon Telescope project openly acknowledge, in their own published work, that current observations cannot completely rule out the possibility that the central object might be a horizonless compact star rather than a true black hole. That admission is what makes this entire area of research so genuinely compelling and so different from typical internet speculation. This isn't a conspiracy theory built on ignoring the evidence. It's a live, active, and completely legitimate area of theoretical astrophysics, built directly on top of the exact same data the Event Horizon Telescope produced. Scientists studying black hole mimickers describe their work as a fast-growing field, precisely because of a fundamental, uncomfortable truth about event horizons themselves. They are, by their very nature, extraordinarily difficult to observe directly. An event horizon doesn't emit light, doesn't reflect radiation, and produces no signal of its own, since anything crossing that boundary vanishes from the observable universe entirely, leaving no trace an outside observer could ever directly detect. Everything astronomers can actually measure comes from matter and light interacting near that boundary, never from the boundary itself, which means, in principle, an object without any event horizon at all could still produce nearly the exact same external signature as one that has one. This is precisely why so many research teams around the world are racing to refine the Event Horizon Telescope's methods add new radio dishes to the network and push toward even sharper, higher resolution images of both M87 star and its smaller, closer cousin at the center of our own galaxy, Sagittarius A star. Expanding the network means adding observatories in entirely new locations around the globe, filling in gaps in the array's coverage that currently limit how sharp and complete any single image can be. A slow, expensive, but steadily advancing engineering effort that could take years to fully realize. Some researchers have proposed that future observations, particularly ones capable of resolving the photon subring, an extremely faint, tightly wound ring of light, theorized to sit just outside the shadow itself, could finally provide the kind of precise measurement needed to distinguish a true black hole from an exotic mimicker once and for all. That photon subring is thought to form as light makes multiple, increasingly tight loops around the central object before finally escaping, encoding subtle details about the exact geometry of the spacetime it passed through. Details far too faint for the original 2019 image to capture, but potentially within reach of the next generation of instruments. Differences in how that photon subring behaves, how variable the surrounding plasma appears over time, and how closely the observed spin and mass line up with the predictions of general relativity's Kerr metric, could all eventually settle this question with far greater confidence than the original 2019 image ever could. Until then, the honest scientific answer is more nuanced and frankly more interesting than either the confident textbook version or the more dramatic online headlines suggest. M87 star almost certainly is a supermassive black hole, exactly as the overwhelming body of evidence indicates. But the reason scientists can say almost certainly rather than absolutely certainly isn't ignorance or oversight. It's an honest reflection of just how difficult it actually is to prove the existence of something defined entirely by the one thing it can never let you see directly. Every image, every ring of glowing plasma, every dark central shadow captured so far is, technically speaking, consistent with a black hole without being definitive proof that rules out every conceivable alternative, a distinction that matters enormously to physicists, even when it barely registers in the popular retelling of the story. That gap between consistent with and definitively proven is exactly where this story lives, and it's a gap serious physicists are actively working to close, one improved observation at a time. The next generation of the Event Horizon Telescope, along with entirely new space-based interferometry concepts currently being studied by researchers, aims to capture the kind of detail that could finally answer this question with certainty, either confirming once and for all that M87 star truly is the black hole the world celebrated in 2019, or revealing something genuinely unprecedented sitting at the heart of that distant galaxy, an object unlike anything astrophysics has ever directly confirmed before. If this deep dive into the hidden uncertainty behind one of science's most famous images fascinated you, like and subscribe, because as the next generation of black hole imaging technology comes online, we may finally learn whether M87 star is exactly what we think it is, or something science has never truly proven exists at all, an answer that could reshape our understanding of gravity, matter, and the fundamental physics governing the most extreme environments in the entire universe.